Hello students, in this video I am going to explain you about Kirchhoff's laws. In simple circuits where resistance, current or potential difference are need to be calculated, we simply use Ohm's law. But in complex electrical circuits where there are large number of resistances, large number of sources of EMFs, then this simple application of Ohm's law is unable to solve such circuits. So, Kirchhoff gave two rules for solving such complex electrical circuits. These rules are known as Kirchhoff's rules. Before using and understanding these rules, we should understand two terms. First is junction or node, other is loop or mesh. So what is a junction? Junction is a point where two or more conductors are connected electrically. That means two or more conductors connection is there, and in loop or mesh it is any closed path in an electrical circuit. So now let us start with the rules. Kirchhoff's first rule or current rule or simply junction rule. See here in the figure, this point will be termed as the junction. Here there are more than two branches meeting together, and on this branch we can place the conductors also. So the first rule says that the algebraic sum of various currents meeting at a junction in a closed electrical circuit is always 0. That means at this junction the sum of all currents either entering or leaving will be equal to 0. That means, look here, the I1 is entering, I5 is also entering, I4 is also entering the junction, but I2 and I3 they both are leaving the junction. So the polarities will be taken like this. The current which are entering the junction will be taken as positive, means I1 will be positive, I5 will be taken as positive, and I4 will also be taken as positive, and the current which are leaving the junction will be considered as negative. Likewise, I have written here I1 minus I2 minus I3 plus I4 plus I5 is equal to 0. Or in other words, you can say that the sum of the currents entering a junction is equal to sum of the currents leaving a junction. That means I can rearrange the above equation. In electrical circuit, current cannot be stored at a junction. This we have just seen. So we can say that this law supports law of conservation of charge. Nothing is stored at this junction. Whatever the currents are entering, few of the currents are leaving. So the sum of the currents entering and leaving is same. So this rule is based on the conservation of charge. Now let us see the second rule. Kirchhoff's second rule, also known as voltage rule or loop rule. The algebraic sum of the products of the current and resistances in each of the conductors in any closed path or mesh, or you can say loop, in a network plus the algebraic sum of the EMFs in that path is 0. See here the same I have written mathematically, that is the sum of all EMFs plus the sum of the product of the current and resistances should be equal to 0. Let us see from the circuit here. See, I have mentioned here the direction of travel. That means we have to move here clockwise. So we can start from any of the node. That means I can start from A, I can start from B, I can start anywhere along the direction of the travel that you have to mention. So here let me start from node A. When we are moving from the node A, we have to come back traveling this entire path to A. Now let us start traveling. From A to B, there is only one resistor, that is R1. So as we have written the product of current and resistance, so here we will write I1 R1. As we are traveling in the same direction as the direction of the current marked, so we will consider here the sign of current I1 as positive. Likewise, I have done here I1 R1. Now from B to C, there is one resistor and one source of EMF. So the current flowing from B to C is I2, and again we are traveling in the same direction as the marked current, so the product will be taken as I2 into R2. Likewise, here I have written. And the terminal of the battery occurring first, here this is the positive terminal occurring first, so we will write it as plus E2, like I have written here. Now from C to D, there is one resistor R3, but we are moving against the direction of the current marked here. That is, when we are traveling from C to D, the current I3 is marked opposite to the path of our travel. So we will write as minus of I3 R3, like here I have written. Then again moving from D to A, one of the EMF is there, so the polarity, the terminal occurring first is the negative one, so I will write minus of E1, like here. Then R4 will be multiplied by the current I4, and as we are moving in the same direction as the direction of the current given, so we will write it here as plus I4 R4. So this will be the complete equation for the voltage rule. Here the net change in energy of a charge after it travels a closed path must be zero, because the electrostatic forces are conservative forces. That is, it is independent of the path taken and only depends on the position of the object. So we can say that it supports the law of conservation of energy. So this is the second rule, Kirchhoff's voltage rule, and in simplified form we also call it as Kirchhoff's voltage law, that is KVL. And Kirchhoff's first rule, current rule or junction rule, is also known as Kirchhoff's current law, that is KCL. Now let us understand both these rules better with the help of example. Here I have taken one electrical network and we have to calculate the current flowing through 4 ohm resistor, and the 4 ohm resistor is placed between B and A. Now let us suppose that the current flowing through R1 is I1 and the direction is as shown. This current you have to mark yourself. Now the current I1 will be flowing like this, but here when it reaches the node B, there are 2 branches. So the current will divide. One part of the current will move towards the flow towards the 4 ohm resistor, and the other part of the current will flow towards the 8 ohm resistor. Let the current flowing from B to A be marked as I2, and the rest over current, that is I1 minus I2, flows through 8 ohm resistor. There are two loops, or you can say two meshes. Let us mark them as mesh 1 and mesh 2, or loop 1 and loop 2. Now apply KVL, Kirchhoff's voltage law, in loop 1. Again we will find one direction of travel, as I have shown here by the arrow direction. We will move in this direction. Let us start from this node, that is node A only, as there is no component in between, so this is node A only. So from here, when we will move, the first terminal occurring is negative of E1, that means we will write it as minus of 20. Then we are moving in the same direction as the current I1, so we will write it as 10 I1, that is the potential difference across 10 ohm resistor, as I have written here. It is 10 I1 and same direction, so positive. Now come back to the 4 ohm resistor, as we are traveling and no component is placed here. So we will come back to 4 ohm resistor. The current flowing I2 is in the same direction as the direction of the travel. So we will write it as 4 of I2, as I have marked here. Now we have reached back to position A, node A, so we will equate it to 0. Rearranging this equation, we will get as equation number 1, 10 I1 plus 4 I2 is equal to 20. Now apply KVL in loop 2. Again we have to start from somewhere. Let us start from here. You can start from any of the node. I am starting from node B, as there is no component placed here, so this is node B only. The terminal occurring first is minus of E2, that means we will write it as minus of 12. So I have written here minus of 12. Now there is a resistor of 8 ohm and the current flowing through 8 ohm is I1 minus I2. So the direction of current is same as our direction of travel, so it will be taken as positive, that is 8 times I1 minus I2. Now going back towards the AB branch, now we are traveling in this direction, that is opposite to the direction of the current I2 flowing from B to A. So it will be taken as negative, that means minus of 4 I2. Here I have written minus 4 I2. As the loop is now finished, that means we have come back to the original position, original node B, so equate it to 0. Rearrange the equation and we will form this equation. Let it be marked as equation number 2. Now we have to solve these two equations 1 and 2 simultaneously. First solving, look carefully, it is 10 times of I1 plus 4 times of I2, and here I need 12 I2 in order to simplify it simultaneously. So I am multiplying the equation number 1 by 3. So what I will get, I will form this equation, that is 30 I1 plus 12 I2 is equal to 60, and second equation is as it is. So when we will add these two equations, I2 term will cancel and we are left with 38 I1 is equal to 72, or in other words I1 value comes out to be 1.895 amperes. Now putting back this value of I1 in any of the two equations 1 or 2 to get the value of I2, I have kept in equation number 1 and we have obtained I2 as 0.2625 amperes. That is the current flowing through 4 ohm resistor, and as the value is coming out to be positive, this shows that the direction which we have marked in the circuit from B to A is the correct direction and its value is 0.2625 amperes. Now let us solve one more question. Here there is a circuit given and we have to calculate the value of the unknown resistance R marked in the circuit. so that the current in the circuit is 0.2 amperes, which is given. What would be the potential difference between the points B and E? That means between these two terminals the potential difference is also asked. For this we have to simplify this part of the circuit first. If we look carefully, this 5 ohm resistor and 10 ohm resistor are in series combination. That means they will form 15 ohm resistance. Now this 15 ohm resistance is in parallel with 10 ohm and 30 ohm. See, I am drawing this part of the circuit, that is this terminal is B, this terminal is E. The leftover circuit after simplification is this. This is 30 ohm. This part is 10 ohm as given, and we have just simplified the series combination of 10 and 5 ohm, which is 15 ohm. So if we look carefully, now these three are in parallel. If these three are in parallel, we can find out their parallel combination like this. So it comes out to be that the resistance now is 5 ohm. That means the equivalent resistance of this part of the circuit is 5 ohm. So we can place it back in the circuit to get the simplified form. The leftover circuit we are having is this, where we have to calculate the unknown resistance also. This is the 5 ohm resistance, and these are the terminals B and E. After simplification of the right hand side of the circuit, this is 15 ohm as given, this is 3 volt, this is 8 volt, and the current given is 0.2 amperes. Now we can simplify the circuit by using KVL. Again the direction of the current is given, so we can move in the same direction as the direction of the current is given, that is the travel direction. So let us start from here. It is plus 3, first terminal is positive, so it will be plus 3. The current direction is same as we are traveling, so 15 times of 0.2, that is the potential difference across 15 ohm resistor. Now we will come to minus of 8 volt. Then coming back to this 5 ohm resistor, it will be 5 into 0.2, that is the current flowing through it, and then the unknown resistor, and the direction is in this manner only, so it will be R into 0.2 equal to 0. When we will simplify, we will get the value of the unknown resistance as 5 ohm. Now we can calculate the potential difference across BE also. Look carefully, potential difference across BE will be V is equal to I into R. I is 0.2 amperes and R is 5 ohm. So simply multiplying, we will get the potential difference across the terminals BE is 1 volt. Now one more practice question. We have to determine the current I3 flowing in the circuit from C to F like this. We have to find this. For this, let us apply KCL, that is the first law, Kirchhoff's current law at node F here. Here the current I3 is entering and both the currents I1 and I2 are leaving the node. So we can say that I3 is equal to I1 plus I2. That means this current is entering and it will be separated in two parts, that is I1 and I2. So let us mark it as equation number 1. Now applying KVL in loop A, B, C, F, that is the upper loop. Now again we have to travel in one direction. This current I1 direction from the 30 ohm resistor will be somewhat like this. It is going to come back in this manner. Let us start traveling from A. So it will be 30 times I1, and that path is somewhat like this. So it will be minus 20 plus 20 I3 and reaching back to A. So we have written this equation. Simplifying further, we will get this equation. Let us mark it as equation number 2. Now applying KVL in the loop A, B, D, E, that means the entire bigger loop. So again we have to travel in one direction. So let us again start from A. So it will be 30 times I1 moving in this way. The direction of I2 is here like this, coming back to D. Now see, when we reach to 20 ohm resistor, the direction of current I2 is opposite to the direction of our travel, because we are traveling like this. So it is opposite to the direction of travel, so we will consider it as minus of 20 I2 as I have written here. Now the terminal which is occurring is positive of 80 volt, so we have taken it as plus 80 equal to 0. Simplify it, we will obtain this. Let us mark it as equation number 3. Now we have to solve equation 2 and equation 3, but here there is one extra term, that is I3, so we will put back the value of I3 from equation number 1 in equation number 2. So after rearrangement we have obtained equation number 4. Now see equation 3 and equation 4. If we simply add these two equations, these term minus 2I2 and plus 2I2 will cancel each other. So we are left with 8I1 on the left hand side, and on the right hand side it will be simply minus 6. So we will obtain I1 as minus 3 upon 4 amperes. Putting this value of I1 in any of the above equations and solving further to get the value of I2, we have obtained as 23 upon 8 amperes. Now to obtain I3, let us put this value of I1 and I2 back in equation number 1. And what was equation number 1? It was simply I3 is equal to sum of both the currents I1 and I2. So adding together we have obtained 17 upon 8 amperes, and that was our requirement. That is, we need to calculate the current flowing through 4 ohm resistor from C to F, that is 17 by 8 amperes. Thanks for watching. Please like, share and subscribe.